Now we're going to talk about binomial distributions. And when we talk about them, we're going to look at three different aspects of binomial distributions. We're going to look at binomial experiments, we're going to look at binomial probability, and then we're going to look at the binomial theorem. But before I jump into that, I wanted you to take a look at this thing right here. Mine's called a hexstat. Sometimes you'll hear it called a Galton box, named after the person who kind of invented it. But what we have here are these little silver balls, and there's actually one gold one in there, but there's 100 of them in here. And I'm going to put them back up here into the top, into this funnel. And you'll notice as they come down, they have a choice. They can go left or they can go right. And after they make that choice, they have a choice again to go left or right, and that continues until they land down here. So this is a device that we can use to kind of demonstrate what we're going to talk about today. So let me get them all back up to the top. Kind of show you what happens when we tip this over. So they're all at the top, and I'm going to flip this over. Now as you can see at the bottom here, there they all kind of went through, they kind of follow this binomial curve a little bit because of how they ended up. Now if I would have cheated this a little bit and turned it one way or the other way, I can make that bottom change just a little bit. It still kind of has that curve to it, but now you notice it was kind of skewed towards the direction that I tilted it. So we're going to talk about what's going on here. We're going to get into the algebra of what this thing is actually demonstrating. So let's start with the idea of a binomial experiment. Binomial experiment has to follow these rules. First of all, there has to be a fixed number of trials. In the Galton box that I showed you, the hexstat, there were 100 trials because there were 100 balls following their path. Each trial has to have two possible outcomes. So every time they hit one of those, they either went left or they went right. There was no left, right, or straight. There can't be three possibilities. It only has two possible outcomes. Every trial has to be independent of one another. So each ball did its own thing. It wasn't controlled by the ball in front of it. And the probability of each outcome is constant throughout the trials. I'm not having two choices here, but then later on I have three choices, then I go back to two choices. It has to be constant throughout. If it's a 50-50, if it's a 75-25, it has to stay consistent. So I did an example with a tree diagram. And this tree diagram demonstrates somebody who we consider a good basketball shooter. By good shooter, I said the probability of them making a free throw is 90%. They are a 90% free throw shooter. And I just did two trials. So the first trial would be one basket being shot. If it's good, if they make it, I used good, so G is a make. 90%. If they miss it, I used an M, 10%. So two choices there. They make it or they miss it. That has no effect on the next basket. I'm going to do two trials. I was going to have them shoot two baskets, and the probability has to stay 90-10 the whole time through. So after they shoot the first basket, we're going to do another basket. Let's assume they made the first one. So now I have a 90% of it being good or 10% of it being missed. If I would have done miss first, I have a 90% of being good or a 10% chance of being a miss. So this is only two trials. So you can see how trying to do a tree diagram for 10 trials or 50 trials would be huge. It's going to take a lot of work. But let's look at some of our results here. If I wanted to know the probability of them making both of them, two good baskets, 0.9 times 0.9 is 0.81. They have an 81% chance of making both. If we talk about making one and missing one, and if I don't care on the order, I could go this route, which is 9%, or I could go this route, which is 9%. So I actually have two ways of one good, one miss, 9% each, so I have a total of 18%. So if it doesn't matter which one is made first or missed first, 18%. And if we talk about the probability of two misses, 10% times 10%, which is 1%. So I have a 1% chance of missing them both if I am a 90% free throw shooter. Now if you add all these up, we would get to 100% of the probabilities. but you can see how this is going to get big in a hurry. So let's take a look at it from a little different point of view. When we talk about a binomial probability, and this is the thing we want to get to, N is going to stand for the number of trials. The repeated, they have to be independent. P, and I'm not sure why they use P, but P is our success rate. Q is our failure rate. Okay, so if you add P and Q up, you should get to 100%. So P is our success, Q is our failure, and X is the number of successes. So if I look at this right here, this says the probability of X. So that's how many successes I want. I do N choose X. N is the total number of trials. X is the number of successes. I take the success probability. Okay, this is the success rate to the X power. That's how many successes I had. And if I subtract N minus X, that would be the number of failures. So I take the failure rate to the power. Let's dive into an example and see if this makes a little more sense. So we have scratch-off cards. They have a 40% chance of winning a prize. So I decide to buy 5 cards, and I want to know the probability of winning on 4 of those 5 cards. Okay, so we're looking at the probability of 4 wins. So if I follow through this and choose X, there are 5 trials because I bought 5 cards. So we've got 5. I'm only choosing 4 to be winners. My success rate. It says I have a 40% chance of winning. That means I have a 60% chance of losing. So my success rate is 0.4, and I'm talking about having 4 successes. Now my failure rate then would be 0.6. If 4 of them are successes and there's 5 trials, then one of them must be a failure. That's where this comes from. 5 trials, 4 winners means 1 loser, 1 failure. So if I calculate this out, I will know what my probability is of getting 4 winners out of those 5 cards that I bought. If any of these numbers change, if all of a sudden I buy cards that only have a 20% chance of winning, this becomes 20, this becomes 80, and it's going to change my answer. If I only wanted 3 winners, 5 choose 3, that means there's 3 winners and 2 losers. If I calculate this out, 5 choose 4, multiply by 0.4 to the 4th, times 0.6 to the 1st, my probability of getting 4 winners, 0.08, 8%. Now, you have to be careful on their wording because if they instead said, what's the probability of at least 4 winners? Not only do I have to do this probability, I would also have to do the probability of getting 5 wins. So 5 wins would be 5 choose 5. My success rate would be all 5, and I wouldn't have any failures. So if I take that and calculate it out, I end up with 1%. So the probability of at least 4 is 8%. Plus 1%, that's a 9% chance of getting 4 or 5 winning scratch-off tickets. Let's take a look at the last type of binomial distribution, is the binomial theorem. And this is where we tie what we've talked about with binomial probabilities and experiments to some algebra. So in black up here, they have the definition of the binomial theorem. If I have a binomial, a plus b to any power, I do n choose 0, a to the nth, n choose 1, a to the n minus 1, and a b, n choose 2, a to the n minus 2, b squared, and I work my way all the way down. Let me show you an example. I kind of worked through one or started working through one so you get an idea of what's going on here. They want to take x plus y to the 5th. So x plus y times x plus y times x plus y times x plus y times x plus y. That's a lot of foiling. That's a lot of box method. There's a lot of algebra there. If I use this binomial theorem, I do 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. I know what those numbers are. 1, 5, 10, 10, 5, and 1. Now I go back and I do powers of x. So this would be x to the 5th. This would be x to the 4th. This would be x cubed. This would be x squared. This would be x to the 1st. And this one doesn't have an x on it. So I go from the biggest power of x, and I get it from here. 5, 4, 3, 2, 1, and this doesn't have any. Now for my y's, it kind of works backwards. I'm going to start at the end, and this is actually y to the 5th, y to the 4th, y cubed, y squared, y to the 1st, and then this one doesn't have a y. So if I put all this together, 1x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5x y to the 4th plus y to the 5th, I have expanded this binomial without having to use much algebra. I instead use the binomial theorem. They're never quite as easy as just x and y. There's always something else in there. Okay, so I threw some numbers in here just to show you how this changes things a bit. So this is dealing with 4. So we're going to have 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. That's how I get those coefficients in the front. And I know those. That's 1, 4, 6, 4, and 1. I know those. Okay, I can use my calculator if I don't know them. Then I've got this 3x that's supposed to be raised to the 4th. So there's a number in there. So this is going to change a little bit. And here I've got a 3x cubed and a 3x squared and a 3x to the 1st. So I've got numbers that are getting multiplied in that are going to change my coefficients. If I take the second half of this binomial, y to the 4th, y to the 3rd, y squared, y to the 1st, and this one doesn't have any y's on it. So I've got some more math to do here, and I'm going to put in my plus signs so you can kind of see where they're separated. It's not as simple as just the 1, 4, 6, 4, 1. I need to take the 1 times 3 to the 4th power. That's a little different. But I still have that x to the 4th there. Then I need to take 3 cubed, multiply it by the 4, so I get 108 x cubed y to the 1st. So I have some arithmetic to do here, but it's way easier than taking 3x plus y times itself 4 times. So now I have 4 choose 2, and I've got a 3 squared that I need to multiply together, so I get a 54 x squared y squared. I've got a 4 choose 3, and I've got a 3 to the 1st, so I end up with a 12 x y cubed. And finally I have a 4 choose 4 and a y to the 4th. Here's the full expansion of 3x plus y to the 4th power. A lot of things to do, a lot of arithmetic, a lot of things to keep track of, but that's why the binomial theorem is here to help us make this a little quicker. Now, sometimes they won't ask for the whole expansion. Okay, they may only ask for part of it. So this one says, I only want the 3rd term of this particular binomial. I could still write them all out. So we've got 4 choose 0, 4 choose 1, 4 choose 2. I could write them all out, but I'm only interested in the 3rd term. So I'm going to focus in right here. And this would be 2x to the 4th, 2x cubed. This one's 2x squared. And if I work backwards, this isn't going to have any, of the second term. This is going to be negative 3y to the first, so that means this would be negative 3y to the second. This is the only piece I'm interested in. So I only have one calculation to do instead of all of them. So I need to take 4, choose 2, which is 6. I need to take 2 squared, which is 4. I need to take negative 3 squared, which is 9. I need to multiply that out. And I also have my x squared and my y squared on there. So if I multiply this out, I get that third term. Now let's take this binomial theorem concept and tie it to the binomial probability that we talked about earlier. So I have a multiple choice test, 4 questions. Each question has 5 choices, A, B, C, D, and E. And my probability of success then, since there's 5 choices, one of them is right, 1 out of 5, that's 20%. That means my failure rate would be 4 out of 5, which is 80%. So if I take this concept of a binomial theorem and apply it to what's going on here. Here's my success rate, here's my failure rate. I've got a 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. My success rate is 20%, 1 out of 5. One of the 5 choices is correct. So here, this would be 0.2 to the 4th power, 0.2 to the 3rd power, 0.2 squared, 0.2 to the 1st, and that wouldn't have any correct. The Q then, if I work backwards, I'd have 0.8 to the 4th, 0.8 cubed, 0.8 squared, 0.8 to the 1st, and that doesn't have any failures in it. So it's just numbers right now. It probably doesn't have a whole lot of meaning. So let's talk about what meaning goes with this. I'm going to guess on this multiple choice. I haven't studied. I have no idea what these 4 multiple choice questions are. I'm going to guess. This right here, 4 choose 0, is I got none wrong. Got them all right. This would be the probability of getting them all correct. Now if I move down here, 4 choose 1, I got 1 wrong. But I got 3 right. 3 successes, 1 failure. This would be 2 correct, 2 wrong, 1 correct, 3 wrong, and all 4 wrong at the end. So if we talk about this setup, I can answer any questions that they may have about this. So if they ask me, for multiple choice, you have to get at least 3 right to pass, and you're going to guess what's the probability of getting at least 3 correct. I'd have to calculate that one and that one, add them up. If they said you fail if you get 1 or 0 right, then I would add up these last 2. It just depends on what I'm looking for with this particular problem, but I can do those calculations. Now, if I would add all these up, I would get 100%. Those are all the different possibilities of what happens, just like the tree diagram and the free throw shooter. But in this case, we're only talking 4 questions, so that tree diagram would have 4 sets of branches. This is just telling me my success rate and my failure rate. So we can apply this idea of the binomial theorem to something that has to do with probability.